Okay. All right. Sorry for all that excitement. You know, you got to take these things seriously. Unfortunately, it's kind of messed up our class more than anything else, but we'll recover. I think what we'll do is we'll work through the introduction to the material today, and then I'll post a video of the stuff we don't cover from last year or something. I'll let you know in email how we're going to work it out, but I think we can probably cover it like that so that we can stay on schedule. Okay, so I'm sorry about the I got the date wrong for the homework due. I think everyone got the message, and I'm sorry about that. It was just because last year the schedule was different, so I just copied the date without thinking. But so the homework is due on Wednesday, then there'll be a new homework on Wednesday. Several people have spoken to me. So in the midterm, some people did very badly, and people understandably feel quite. That can be quite disheartening. And people are saying, "Well, am I even going to be able to get through?" And so I spoke to some people last week, and I tried to reassure them. But the other thing about the midterm is that some people did incredibly well. I mean, I got several people did amazingly well. So the whole thing is a little bit strange, and I don't know quite what to do about it. But here's one thing. Here's one thought I had. I've heard in other classes you'll have this thing where it's like, there are some number of grades, and we'll take the best n of those grades. It's difficult to do that in this class because there are only 4 components. But we could do something like that, where we have the midterm, the homeworks, the final, and the project. And the midterm and the homeworks are 20%, the final project 30% each. So what I'm saying is we could break up the grade into 10 pieces, each worth 10%. So there are 2 for the midterm, 2 for the homeworks, 3 for the final, 3 for the project. And then your final grade, we drop the least good of those, right? So then we have 10 pieces. They've got 10 scores, 2 of the scores, 2 pairs and 2 triples. But we take one of the parts that's the lowest and just drop it. So then it's like the net result is if the midterm is the thing that you did worst on, then the midterm only contributes 1/9 of your final grade rather than 1/5. But if you did well on the homework, then if you did well on the midterm, then the midterm contributes fully to your final grade. I've never done this before, and I'm a little bit anxious to mess with the grading scheme just because there's always unintended consequences. But if you have any, I like the idea that I like the idea that we're removing an outlier, at least removing the impact of an outlier, because outliers happen. If you see any problems with that scheme, or if you have any comments, then let me know. Okay? Great. All right. Anything else before we move on? Okay. So I'm planning to go until like 11:30, so we'll overrun class time a little bit, but I think obviously we've got the rest of the day to get on with, so we'll finish before the next class. Okay, so we've been talking about filter design. We've been talking specifically about IIR filters, filters with poles, and I asserted that the way we do this is by using the mathematics that was developed for analog filters, continuous time filters. And the reason being that basically the idea that the filters we really wanted to have are these filters that have ripples, but the ripples are equal depth, right? That's quite a complicated thing to arrange. Or they're smooth, but they're as flat as they could possibly be. That also seems like that's something that you can define mathematically in this case by taking a large number of derivatives at the extreme at 0 to be 0 or something like that. Basically, there's one mathematical equation, there's one polynomial or one rational polynomial that achieves those particular criteria, and even though the domains are different between the continuous time and discrete time, in some sense it's going to be essentially the same solution. It may look a little different, but mathematically you're trying to optimize the same thing, that is the smoothness or the ripple depth, and so you're going to end up with the same solution. That's basically what happened. And of course, the solutions are quite sophisticated. But once they've been found, and we can just use them. So we went through the solutions of how this is done in the analog domain. The 4 types of filter: the Butterworth, which are flat in both domains; Chebyshev 1, which is flat and then which has ripples and then is flat; Chebyshev 2, which is flat and then has ripples; and the elliptical, which has ripples in both passband and stopband. So now we basically know how to do that, and we also went through how you can translate those into, translate low-pass prototypes into high-pass, and then also band-pass and band-stop by using transformations on the S domain. So now we're at this point like, okay, fine, now we can do these continuous time filters. How do we generate our discrete time filters? And as I mentioned at the end of last class, the principle is very similar, that we're going to think about a mapping between these transform domain variables, between the filter that we just defined in the S-plane. And by designing this filter in the S-plane, what it meant was we had a system where all the poles were stable, so they were on the left-hand half plane, and the values on the imaginary axis had these very closely controlled parameters that they either had this smoothness or these ripples of controlled depth. So if we could only figure out a way to take those same properties and make them show up in the analogous way on the z-plane, then we'd be set. And what that means is we've got this polynomial, this rational polynomial in S. It is completely defined, apart from a gain constant, by the location of its poles and zeros in the S-plane. If we can figure out how to move those poles and zeros onto the z-plane such that the poles remain stable, which in this case means they remain inside the unit circle, and the magnitude response, or the frequency response values, those values on the imaginary axis, now become the frequency response values here, then we can have a filter which will still have these flatness and ripple characteristics. And all we have to do is define a relationship between S and Z that achieves this point, so that every value of S becomes some value of Z, and then if we have a function where we do the substitution of this function of Z for S, then, assuming we get it right, then there was some point here where, h of S was some value. If we map the same point here, then G of Z will be the same value. And in particular, if h of S is, say, a pole, meaning that h of S is an infinite value, then this will still be a pole in the z-plane. If h of S is a point on the imaginary axis, then it'll be a point on the unit circle. So all we have to do is come up with this mapping, and hopefully everything will work out. And so this is just saying what I just said. We're trying to, these are the two parts we care about, the left half plane and the frequency axis. But notice that there's a little bit of a problem here, which is that this imaginary axis is infinitely long, but we want to map it to this finite length. The positive part of the frequency axis is this positive part of the unit circle, the discrete time frequency space. And then, there's this thing we know, the discrete time frequency is basically periodic, that there's this continuity between the highest possible frequency plus pi radians per sample and the most negative possible frequency minus pi radians per sample. Whereas on here, those 2 points are like at plus infinity and minus infinity. So it's like, how are we going to make them stick together? Because they have to become adjacent when we do the mapping. But it's possible. And so the solution that we use, the mapping that we use, is the bilinear transform. It's bilinear because it's 2 linear terms, but it's the ratio of 2 linear terms. So it's not actually a linear mapping, which of course it couldn't be. So if we define S as Z minus 1 and Z plus 1, then if you rearrange that to make it as a function of Z rather than a function of S, you get this, Z equals 1 plus S and 1 minus S. So it's a one-to-one mapping. It's a unique one-to-one mapping between the whole of the Z-plane and the whole of the S-plane. So looks pretty simple, but it's not trivial to think about because, it's the ratio of these two things, plus 1, minus 1. I don't know. It's not, I don't look at that and immediately know what it's going to do. But let's check that it has the properties that we wanted. Okay, so we wanted the frequency axis to get mapped, the imaginary axis to get mapped onto the unit circle. So if we're on the imaginary axis, that means S equals j omega, right? For some frequency omega, it's a purely imaginary value. So from this, then we get, well, z is going to be 1 plus s, 1 plus j omega, divided by 1 minus j omega. And so here we have the ratio of two complex values. Their real parts are both 1. Their imaginary parts are both omega, but they're plus j omega and minus j omega. So their magnitudes are the same. So the actual magnitude of this ratio of complex values is going to be 1. So we do have the magnitude of z equals 1, which means that z is going to fall in the unit circle. The actual point where it's going to fall in the unit circle will depend on omega, right? Because it'll be the ratio of these two angles here. It'll be, we'll see what it is in a second. But its magnitude will be 1, so it is in the unit circle. So that does what we wanted, right? It maps any point that's pure imaginary ends up on the unit circle in the z-plane. So that's great. Then we wanted to check that the poles that were in the left-hand half-plane and the s-plane end up inside the unit circle. So we did the same thing. Now, in general, we're going to say, well, let's have a general Cartesian form for the point on the s-plane. So sigma is the real part, omega is the imaginary part. So then if we put it into the mapping here, we get the real part is 1 plus sigma, and the imaginary part is 1 minus sigma, and then we've got the real part of the numerator is 1 plus sigma, and the imaginary part is omega. The real part of the denominator is 1 minus sigma, and the imaginary part is minus omega. If we then look at the magnitude squared of z squared, right, it's going to be the magnitude of this part plus the magnitude of this part. So, we get the magnitude by squaring the real and imaginary components. So this is the square of the real component. This is the square of the imaginary component. Do the same on the denominator. And what you can see is that they only differ in this sigma term here. And if sigma is negative, then this one's going to be the negative one, this one's going to be the positive one. So this one's going to be more negative than this. And then provided this thing doesn't go super negative, provided if this whole sum ends up being positive, then the fact that this one is more negative than this one means that this one will be smaller, magnitude will be smaller. But this term here is just the square of 1 plus sigma, so it has to be positive. So even though this individual component is negative, it's never going to be larger than sigma squared plus 1. So this whole term is going to be positive, and it's going to be, negative for sigma larger than this term, where sigma is negative. So it's going to be smaller than this term. So the magnitude squared is going to be less than 1. So this point lies inside the unit circle. Again, I feel like that was kind of a slightly confusing argument, but the point is it's easy to see just by looking at this magnitude squared that if sigma is less than 0, which means that s was in the left-hand half plane, then the magnitude of z is going to be smaller than 1, which means the poles lie inside the unit circle. So, okay, checking these 2 points seems like this is doing our job. It's every point in s lands up somewhere in z, and it's a one-to-one mapping, so it's a unique mapping, because we can write the equations both ways. I guess we got a bit of a problem when s equals 1.
Yeah, also when z equals 1, then it's 0, right?
When z equals 1, it's 0. That's okay. When z equals minus 1, we've got it mapping to infinity, which, typically we don't like. But actually, as prudent engineers, when doing math, we try very hard to avoid zeros on the denominator. But mathematicians don't give up when that happens, right? They say, yeah, if you have a 0 on the denominator, it means you have an infinity, and then it gets messy. But the point is that you can handle this mathematically, and it turns out that this does work. But what's strange is that we're saying this point, z equals minus 1, maps to infinity on the s-plane, and it by the weird math of infinity, it's both plus infinity and minus infinity at the same time. And that's the point that the frequencies, which are both the highest possible frequency and lowest possible frequency in the z-domain, that point at z equal minus 1, the back of the unit circle, does end up mapping to both frequencies. We'll see. We'll visualize this in a second. And so s equal 1 maps to z equal infinity. We don't care that much about s equal 1, right? It's some position in the right-hand half plane. But we have the same property that the the points at infinite radius on the z-plane actually end up mapping to a single point on the s-plane. So having noted those problems, that it's okay, everything's okay. So here's my attempt to visualize this. What I've done is on the s-plane, right, this is just the s-plane, there are 4 quadrants, and I took a bunch of, just took a uniform set of points here and plotted them each with an x, right? So I just took every 0.1 between 0 and 3 or something, and then did it for all 4 quadrants. Then I took that point, I put it through the bilinear transformation to find the equivalent point on the z-plane and just plotted it again with a blue x. And so as you see, what's happened, well, what's happened is that this whole thing has been sort of stretched around like this. And so the blue first quadrant has been sort of stretched out to cover this whole outside of the unit circle above 0. And then the cyan quadrant's now outside of here. And the green and the red have been sort of squeezed to fall inside the unit circle. And in particular, these 4 outside points end up sort of all pointing towards each other here. So this corner here is this cusp here, and back here it's this one, and they're all being sort of pulled in to point into the same place. Because if we started going out even further, going out to infinity on these points, we're all going to land up at z equal -1. This is where all infinities end up in this mapping. The boundary between blue and red, which is the positive frequency axis, now you see, so this point here, these 2 points which are closest to 0, land up here, right? 0 maps to here because it's z is 1 plus s on 1 minus s, so if s is 0, then z is 1. So 0 lands up here at the origin, which is fine, that's where we expect it to be. And so these 2 points here land up being these 2 points here. They're very stretched apart, right? It's very nonlinear coverage of the space. But then the boundary between them is the unit circle. So that's saying the imaginary axis here gets mapped to this top half of the unit circle as we expect. And similarly for the negative frequency axis goes to the bottom half of the unit circle. So, that gives you some idea, okay, this is how we do it. This is how we can manage to meet all these criteria, and in particular, this weirdness about what happens in infinity. Although it's clearly it's like, that's such a weird thing to look at.
This mapping is specific to the function, right?
It's the mapping is specific to the function.
We are having infinity on z is equals to -1.
Right.
Depends on the pole which we get from the equation.
No, it doesn't. We haven't said anything about what particular function of s we're trying to map. We're just saying that if we have a function of s, for instance, a rational polynomial in terms of s, if we just say, well, actually s is z minus 1 and z plus 1, so let's say I had this function which I put in s, I get some value out. And it's like, oh, well, actually I'm getting s from z. So I have some value of z, then I get my value of s, then I calculate what f of s is. Well, I can eliminate s from that. I can just substitute into my equation, wherever I see s, I write z minus 1, z plus 1. And if it's a polynomial, I'll get a new polynomial out, which is now a polynomial of z, but it has the same answer. I put the z in, I'm going to get the value out. And so it's just defining a relationship between these 2 planes, such that wherever I would have chosen a point on one plane, there's a point on the other plane, and the function will be the same regardless of which domain I calculated in, if I relate them this way. So even though we're kind of short for time, I wanted to show you this YouTube video because I found this nice video that visualizes this stuff. Where is it? Here we go. And it turns out, well, it's a little bit more general, but it has this way of understanding this mapping, which helped me a lot. So let's see if we can just watch this. Okay. So you see that they're dealing with this. Yikes.
With applications from brain mapping to
What's going on here?
turn each point on the plane to a full They're built in 4 basic parts. The simple translation.
Wow.
Rotation.
Okay, I can do the narration. So the point is that there are these these different the starting point we turned off, starting point we started from, which was this bilinear transformation. It covers all this space of transformations. Now the rotations and scaling and stuff and translation are straightforward. It's this weird one, which is this, this, I forget what they call it, but it's basically this way when we turn everything inside out, when we invert it out. That's the one that's weird to think about. And you can see that's the one, that's basically the only one that is happening in the bilinear transform that we talk about, because we stay centered. Well, I guess not. Anyway, but that's the one that's... Now, here's the trick, right? That now if you think about this as the result of a projection onto the plane, if in particular you have it as the projection from points on the surface of a sphere, where the sphere is illuminated from this point right at the top, and then if this were the shadow of that, this coloration on the surface of the sphere, well, if you move the whole sphere around, you get translation. If you move it away from the plane, you get scaling of the whole thing. And if you rotate the whole thing around its axis, you get rotation. But the trick is what happens when you start rotating the sphere. So there's some set of points on the sphere which are kind of in a complicated place, but they're in the place that will give you the grid when you start off. When you rotate it, when you turn it upside down, you get this bilinear transform. So that's basically what we're seeing. It's like it's a single, in this sort of intrinsic space on the surface of the sphere, everything stays the same. It's just that the way we're used to thinking about it is one way, and then when you turn the sphere upside down, you get it a different way. And that's basically what's going on with this bilinear transform. I mean, this is just mathematical sleight of hand, right? You could define the points on the plane as coming from any arbitrary function of whatever you liked. But when you do it in terms of this idea of projecting points from, the connection between some point on the top of the sphere through a point on the sphere onto a plane, and then think about what happens when you rotate the plane, you get this particular transformation. So clearly there's something intrinsic about, what actually happens. And it makes it seem less completely arbitrary why we do this mapping. It is something that has some kind of connection to real geometry. There's no particular reason why that's, why do we have a sphere? The point about that is that, it turns out that if you think about that sphere, I mean, I don't want to get into this too much. If you think about that sphere, and the light right on the very top of the sphere, then every point on the plane below the light results from that light passing through one point on the surface of the sphere, right? It has to go through part of it, but if it's right on the surface, it'll only go through one part. And then, so it's a way of mapping the entire infinite plane onto the surface of the sphere, and then it turns out that now if you rotate the sphere, you can change what that mapping is, but still there's only one mapping of each point. And so that's the nice property about this. And it turns out with that mapping, we get the relationship between these 2 points. But of course, the only part that we cared about was this, preservation of the unit circle, imaginary axis to unit circle, left-hand half plane to interior of the unit circle. It just happens to be this is mathematically the simplest way we can do it. Yeah.
Not all points in the left-hand side of the S-plane are mapped to the unit circle. Like, a lot of points are inside the unit circle as well.
No, they're all the points in the left-hand half plane are inside the unit circle.
Not on the unit circle.
Right. The only points that are on the unit circle are these points exactly on the imaginary axis. Right. So it's a line. This straight line here becomes this circle here.
So the main motive of going to bilinear transformation is to get a unity magnitude response, or is it like...
It's not a unity magnitude response. let's carry on, and you'll see what happens. You'll see why it's to get whatever values we had for the response, which would be, you know, this nice elliptical filter with its equal-sized ripples. Have those equal-sized ripples show up for values of z equal e to the j omega, for values of the frequency response of this system after we've done the transformation. Okay, so so we've seen that the frequency response values of the S domain are going to show up in the frequency response values of the Z domain, but we haven't seen exactly where. But we can do that because we can just say, well, if we've got our value on the unit circle, Z equal e to the j omega, little omega, we can figure out what value of S that's going to map to. We assume it's going to map to something on the imaginary axis because that was the whole point. But let's just plug it in and see. So S is 1 minus Z and 1 plus Z, 1 minus Z to the minus 1 and 1 plus Z to the minus 1, if we arrange it that way. When we plug that in, we can do this thing, you know, when we get 1 plus e to the j omega, we can make that e to the j omega on 2 times the two conjugate parts. And so the 1 minus 1 becomes 2j sine omega. Let's just check. Hang on. S equals, we have 1 plus e to the minus 1 and 1 minus e to the minus 1. Okay. So here we get the e to the minus j omegas on 2 cancelling out. And I think there's a minus sign that cancels out. But we end up with the sine terms, the j sine terms on the top, and the cosine terms on the bottom. So we end up with this ratio of sine to cosine, so we actually get the tangent. But we get j times the tangent of the angle. So we do indeed get something that's pure imaginary, as we needed in the S-plane. But here's the actual frequency it corresponds to, because like in the S-plane, the value, the imaginary value on the imaginary axis is the frequency in, you know, radians per second or whatever. But it's related to the frequency in radians per sample through the tangent function. So we have omega equals tan of this, or big omega equals tan of little omega on 2, little omega equals 2 arctan of big omega. And if we draw the tangent function, or the arctan function like this, it's this thing with asymptotes, right? That if omega is the arctan of big omega, then we can make big omega, because, you know, the tangent of something can become infinity. So the arctan is going to be bounded even as big omega goes to infinity. In fact, the arctan, you know, the arctan of infinity is pi on 2. But when we multiply by 2, we get something that tends to pi as omega goes to infinity. And this is exactly what we wanted, right? The continuous time frequency can get as large, it can be infinitely high. It can be infinitely many cycles per second or radians per second. But the discrete time frequency, if we go beyond pi radians per sample, then it starts aliasing, and we can't do that mapping because we need that value beyond pi to be the same as this one here. So this mapping ends up compressing the entire infinite frequency range of continuous time into this finite frequency range of discrete time from minus pi to plus pi radians per sample. And it does it by, you know, taking these higher frequencies and compressing them into increasingly small and smaller intervals of the discrete time frequency range. Yeah.
I have a question. So what happens if you have a complex pole? Would the angle from the S-plane convert to what you said for the...
Yeah, what happens if you have a complex root? The idea is, the principle is, h of z for the appropriately mapped value of z will be equal to h of s for the equivalent value of s. Not just its magnitude, but its complex value. So the overall phase, the angle of the imaginary, you know, this complex function at that particular point will be the same. So if we have a point in the unit circle and it's got some value and it's got some phase, that phase will be the same at the mapped frequency. And you know, it has to be consistent, but whatever it is, when we move the poles around, everything's going to work out. It's kind of, you know, I think I have the same intuition as you, which is like, oh, well, I believe that we can get the magnitudes right, but we're changing the whole shape of the frequency axis, so does that mean we mess up the phases? But no, the phases go along with the magnitudes, and everything remains consistent. Yeah?
I just have a question. So we know that h of z, or h of say e by j omega. It's
Yeah.
basically it always has this periodicity with respect to pi. I mean, it always goes
Yeah.
back.
Yeah.
Right? Now, but I'm actually not able to get that equation right into this plot where we actually make this continuous time.
Yeah.
I mean, we get this discrete time from this continuous time.
Yeah.
And
Yeah. So the question is,
why don't we see any
yeah.
folding? In
Well, so that,
this?
okay, that's interesting. So the point is, like, we know that when we end up with our frequency axis, if we actually plot h of e to j omega, like little omega as a function of omega, we can plot it for any value of little omega, and it's going to be periodic, right? So wait, there's nothing here that's giving us that periodicity. Well, actually, I mean, I don't know. I don't know how good an answer this is. The way to really think about it is like, well, that periodicity just comes from looping around the unit circle in the z-plane, and so it's like once you go more than one time around, it's not really a different value of omega. It's because e to j omega has the same complex value. But I could have, the tangent function we can calculate for any value of theta, right? And this is tan theta, and it's got this asymptote, right? The tan function, remember, is the it's the opposite on the adjacent, right? Yeah. So here's theta, here's the opposite, and here's the adjacent. And so as theta goes up to pi on 2, this line becomes infinitely long, so tan becomes infinite. So this is pi on 2 here. But, but you can still, I mean, I don't know. This is how I learned it in, like middle school or whatever. But you can think about it going greater than pi on 2, and then you have and then it's like the intersection with minus, there's an A here and an O here. And it becomes negative, right? So at pi on 2, it's infinite, but then it goes back round and comes back like this, right? And so for every value of theta, I keep getting a tan function. So then I can get an arctan function, which, this is the one I'm looking at. But there's also this one here, right? And so for a single value of omega, big omega here, there are actually multiple values of little omega where the relationship holds. And that's, if you like, the periodicity, that a single function, a single frequency value in the original continuous time frequency maps to a large number of frequencies in the discrete time frequency, even though it's only one point in the z-plane itself, because a single point on the unit circle in the z-plane does actually represent a lot of different, an infinity of different aliases. Okay. All right. So here's the relationship, and what does this actually mean? This is the kind of this is how it boils down. We start off with a system in the continuous time with a frequency response. Here I'm just plotting the magnitude, but it's both the magnitude and the phase that has some shape in the, has some shape. Here I'm plotting it as dB. This is some kind of, I think it's actually, it might be an elliptical bandpass filter, or it could be a Chebyshev 1. Chebyshev 1 or Chebyshev 2? Chebyshev 2 bandpass filter. So it has ripples in the stop band here, has a bunch of ripples here below the pass band, and then actually has some ripples here above the pass band, although they're kind of very spread out, and that's just the nature of bandpass filters in continuous time. It has some zeros, and it has some maxima. And the point about, what we like about this filter is all these ripples have the same depth, both above and below the pass band. In fact, there are going to be, if there are, because of the way that bandpass filters are constructed in the continuous time. No, I don't know what this is actually. Then I think I faked this filter somehow. Okay, there's some filter here, but it's a polynomial. It has equal size ripples in the continuous time domain. It has 3 zeros here and 1 zero here. It has, it has intersections with, it has a maximum frequency here. This is defined by a polynomial in S. We can substitute z plus 1 and z minus 1, or whichever way around it is, for S in that polynomial. We get a polynomial in Z, which is the same order as it happens, because, if we got S to the n, then we're only going to get Z to the n's coming out of this thing. We can evaluate that thing's magnitude response, evaluate it on the unit circle in the Z-plane. We get a set of filters, we get a magnitude response, and every point on this magnitude response maps to, corresponds to a point on the magnitude response in the S domain. And here's the relationship, this arctan relationship. And so if I have some, have some frequency here, which is the largest gain, has a gain of 0 dB, I can look up here. I find little omega as 2 arctan of big omega. Here's the 2 arctan function. I map across here. I get a value of little omega, and it's the maximum of my magnitude response on my mapped function. But what's happened is because this function, it compresses frequencies closer together as they get closer, as they get larger in continuous time space. These low frequency features down here have been sort of stretched out, and this high frequency feature up here has been compressed in, right? So that even if I can keep going to very, very high frequencies, I can keep mapping, but they're still going to be, they're still going to land up in this last little chunk of the little omega space up until pi. So it ends up looking kind of different. The shape looks a little bit qualitatively different, but topologically it's equivalent, if you like. It has the same number of maxima and minima here, and they're at the same magnitude, right? So here they're minus 22 dB, here they're minus 22 dB, because it's the same values, the same complex values coming out. And then it has a bunch of ripples in the stop band. It has a pass band with a maximum of 0 dB, and then it goes back to a stop band, which is at the same, by construction, is at the same dB level here. I mean, we could have designed any filter. We didn't have to have an equiripple filter. But because we know how to design equiripple filters in the analog domain, and that's kind of like a very precise and delicate thing, now we know how to generate magnitude responses with equal-sized ripples in the discrete time domain just through this transformation. The frequencies that the frequencies of the passband are something else. There's not just some scaling of the frequency axis. It's this nonlinear mapping of the frequency axis. But as long as we know how to make filters with these ripples at the right depth, then we can figure out how to move around the actual frequencies to get the frequencies that we want. We can solve that problem. The trick is just having any path to coming up with these filters with pre-specified desired magnitude responses. So and in particular, the parameters that we use to specify the magnitude response, the epsilon, the ripples in the pass band, and the alpha, the A, the worst case attenuation in the stop band, they're the same, right? It's the same depth of ripples here, the same margin between the pass band and the stop band here. So we can just take those design parameters and plug them into, take them from what we want to get out, plug them into the analog design procedure, and we get the right filter out. It's just the frequencies that are a little bit tricky, the frequencies we have to change. So here's how we can actually build,
So basically what you're doing here is we're actually getting we know the analog response and we're mapping it into a proper. So why can't we just do it in a way that we assume an n-tap FIR filter or an IIR filter, and then just use some iterative algorithm to actually just make this response, and then just do some curve fitting or something, and then do an iterative algorithm to actually find those coefficients, FAR coefficients of that FIR filter.
Yeah. So
how is it different? Why can't we do that instead of doing this?
Okay. So the idea is, if we have some shape that we want to achieve in the discrete time frequency response, we could draw it, and then we could just, you could do something like taking the inverse DFT to get the corresponding time domain that this corresponds to. And that works fine. And that's, when we talk about FIR filter design, that's basically how we do it. Not exactly, but because, okay, here's the problem. Well, I know I want to have a bandpass response with, some pass band around 0.5 pi and ripples at around, 20 dB down in the stop band. But I don't know exactly where those ripples are going to be. All I want to say is you can have ripples, and they should be, below 0.45 pi, and they should be 20 dB down. But I don't know exactly which frequencies they're going to land up at. So I can't draw this thing ahead of time. It turns out there is one, filter that has this many poles, however many poles it is, 1, 2, 3, 4, 5, 6 poles probably, that has equal-sized ripples in the stop band. But it's not obvious where they're going to be. If I say I want it to be these size ripples and exactly at these frequencies, well, I could probably find the filter that will get closest to that. But if I let the positioning of the ripples be whatever is best, then I can find the single filter that has the best performance given that number of ripples, but then I'm letting it find its own frequencies. So that's the special property of this filter. It's a, whatever it is, 6th order polynomial in Z. It has equal sized ripples, and it has the best possible margin between the passband gain and the stop band gain. Not this particular filter, but if I design a filter that was the transformation of an elliptical filter, then it's the best possible one with that many ripples of those at that depth. And so there is only one polynomial in the Z-plane that optimizes that property. Right? There's only one best one. And by starting from the one that optimized it in the S domain, which we've already established through this math, and then doing this transformation, we land up with the one that's optimal in the Z domain. I haven't proven that in any kind of rigorous way, and I would have trouble proving that. But it feels right. It feels like, okay, yeah, I can sort of see that when I move these poles around, I get these filters, and then, if I mess with this a little bit, then things start going wrong. For instance, the ripples start being not equal depth. But if my constraint is the worst case ripple, then once I start making them unbalanced, then the worst case becomes dominated by one of the ripples. Here, it's optimally balanced between all the ripples. So if I have some way of getting these equiripple responses in the Z domain, then that's going to be my solution. And then it doesn't really matter how I get to them, because there is, if this truly is the optimal filter, which it is, under the criteria of equiripple in this case, it doesn't matter how I get to it. It's always the same answer. There's only one optimal answer, so I can get to it by any means. So there could be some iterative way of okay, I'm going to put down these poles in the Z domain. I'm going to now just do gradient descent, try and find places that'll make the poles equal depth and move them around. I'm sure you could come up with a scheme like that, but this is actually closed form. That here we can do it without iteration. That we have the math to actually find out the exact polynomial in the S domain, and then we have a way of transforming it into the Z domain so we get the answer straight off. It's, in a sense, once we've established that there is an optimal filter, it doesn't really matter how we get to it, but this is probably the simplest way. Okay.
So this is more for the ease of, it's more less complicated.
At this point, it's just a way of doing it. Initially, the reason to do this would be you don't even necessarily know if what you're trying to do exists, right? I don't know. This is before you can start off trying to optimize something, you have to prove that there is an optimal answer, and so you have to come up with something. I think with the way we've defined it, we can define a criteria that has to be optimizable. But the thing is, there's quite a lot of math behind this that makes more sense, I guess. Something like that. Okay, so let's just quickly go through this procedure, just to try and make it clear what we're doing. So we have, we're trying to build a discrete time filter, right? So we've got some specifications of the filter we want to build, but now it's specifications in the discrete time domain, but they're basically the same. There's the stop band attenuation, pass band ripple, and then the stop band edge and the pass band edge, some frequencies, but these are now in discrete time frequencies. Well, we know what's going to happen if we take a continuous time filter, put it through a bilinear transform. It's going to warp the frequencies in the continuous time to discrete time frequencies based on this relationship, this tangent or arctangent relationship. So we can actually pre-warp these frequencies that we want to get as the output, such that we get these continuous time frequencies that when we then actually put them through a bilinear transform, they'll land up where we want. So now we do the forward warping here. We take the tangent of these discrete time frequencies to get our continuous time frequencies, which we're going to use for our design. They're kind of notional. They're in this kind of artificial space. But we can calculate them. We can plug them into our analog design tools. So now we've got a set of specifications for an analog filter. We can design the filter, and we get some polynomial in S, which is the outcome of our continuous time design tools. Now we've got the filter, we just plug in the bilinear transform substitution here, we get a polynomial in Z, and then because everything was, because this transformation preserves the frequency axis, and because we set the actual values of the frequencies so that when we put them to this nonlinear mapping, they'll end up in the right place, we just end up with the digital filter that we wanted in the first place. So it all works out. So let me just go through this specific example here. I'm not sure. Yeah, okay. So let's say we want a low-pass filter with ripples in the passband at 1 dB depth, a passband edge of 0.4 pi radians per sample, and a stopband edge with at least 40 dB rejection at 0.5 radians per sample. I think this is one similar to one we looked at before. This kind of filter with ripples in the passband, monotonic and stopband is Chebyshev 1. So the only thing we have to do now is we have to do this warping. So now we've got omega p is 0.4 radians per sample, omega s is 0.5 radians per sample. The mapping is that big omega is tan of little omega on 2. So big omega p is just tan of 0.2 radian, 0.2 pi, which is some value. I mean, it's a big omega, so it's in terms of radians per second, but they're kind of these. This frequency has nothing to do with anything, right? It might be, it's not even, it doesn't even, normally to relate radians per sample to radians per second, we'd go through a sampling rate, but there's no sampling rate that does this mapping here. It's to do with this tangent function. But, you know, in some nominal continuous domain, here's a frequency, here's the stopband edge, which in this case just happens to be 1 radian per second. For the, you know, we can convert these ripple specifications in dB to our epsilon and A. And then we, if we're designing Chebyshev 1 filter, we have to figure out the order of the filter. So we do our design equation here. Gives us an order which is just over 7. So unfortunately, we need to use an n equal 8 filter. That's OK. And then we design the analog filter. Then we do the substitution for for S to convert h of S into h of Z. We end up with a discrete time filter. Here's how doing this in MATLAB. So here I have the order, n equal 8. The passband edge, which, you know, is actually, for the Chebyshev filter, is just simply the, you know, the edge. It's the passband edge that we designed. It's the point of the last ripple where it crosses the 1 dB threshold. And then so here's the, using MATLAB to design a Chebyshev 1 filter in the analog domain, in the S domain. So I get up my polynomial coefficients for the analog filter. And then here, MATLAB will actually do the algebra of substituting in the bilinear transform and coming up with the new polynomials in the Z domain. This is, you know, this is mechanical. It's just for every S, you replace 1 minus Z, 1 plus Z, and then rearrange, but you end up with new polynomials. There's a 0.5 here. You can scale this arbitrarily when you do this to get the one that we use, right? We could have, instead of designing to these frequencies, we could have designed to double these frequencies. We would have got the same filter, basically, but then we would have had to map it differently. So 0.5 is just some, you know, it doesn't mean anything deep here. We get this filter out. And then we can plot these frequency responses, and here's the continuous time frequency response, which is the, you know, the Chebyshev 1 filter that we've seen before. Here's the discrete time one, and it looks very much the same. It has these, you know, just barely visible 1 dB ripples, and it's a low pass. Of course, what's happened is that this long tail over here has been actually condensed, so you actually get, you know, it goes all the way to infinite frequency. Let me just, I mean, that's kind of what happens when we go to MATLAB, but just one thing I didn't plot there was, this is, I just did that. If we look at the pole 0, if we look at B and A, B, well, let's look at the pole 0 diagram. So I'm actually going to use Z-plane, but these are actually S-plane things. And so here's our Chebyshev 1 filter, which we're familiar with. Ignore the unit circle. It's this sort of squeezed-in set of semicircle points to give us ripples in the passband and monoticity in the stopband. And if we put them through, so now we had the discrete time polynomials come from this bilinear transform of that rational polynomial. If we look at the poles here, now they are relevant relative to the unit circle. here are the poles which have been mapped, and they're still sort of getting close to the inner circle. They've been stretched out a bit. But you can see they're going to give us ripples in the passband. But now we've got this thing going down to stop band, and lo and behold, we've got 8 zeros showing up here. They actually should be actually on -1, but because of numerical problems, they've been slightly distorted out. But you could say, well, the S-domain polynomial had zeros at s equal infinity, because if you set s equal to infinity, then the polynomial would have given you 0. We don't normally worry about those. When we do the mapping, those points at s equal infinity land up at z equal -1. So now the zeros appear, so we get this filter with this response that actually goes all the way to negative infinity for little omega equals pi. So that's, that's showing that it works, right? And that in particular, that the shows that the magnitude responses are very similar. In this case, they look very similar, whereas in the example I showed, they were more obviously warped. But in particular, we can get a magnitude response, and we can control it, so it does have this breakpoint at 0.4 pi, just like we want it. We don't get some arbitrary frequency coming out. OK, any questions about that stuff? All right, so I'll figure out what to do with the rest of this lecture and let you know.